Well, that's as far as it goes. You have the limit now. That's the slope, the derivative. Yes. Right. Yeah, one of the x's on top of one of the others. So if I put 4 minus 1 equals 3. Let's look at another one. Another example. We'll find the derivative. No, all I asked you to find the derivative. That was it. Differentiate the function x over x minus 1. Let's work this out. We first have to find the f of x plus h. So limit of x plus h minus f of x over h. So limit x plus h minus 1 over x under x plus h minus x minus 1. So this entire denominator has to multiply up there. This denominator multiplies up there. So we know our common denominator is going to be x plus h minus 1 times x minus 1. That's the common denominator. X plus h times x minus 1. X plus h minus 1. I just cross multiply pretty much. Limit as h approaches 0. I don't need the inside parentheses there. If I multiply these two, what do I get? When I FOIL those two, what do I get? X squared minus x plus xh minus h, and distribute negative x to everybody in there. So negative x squared, negative xh, and positive x. Simplify the numerator. X squares cancel. The xh's cancel. And the x's cancel. X plus h minus 1, x minus 1. And on top, all we have left is negative h. Everything else canceled. Reciprocate the bottom. Negative h, x plus h minus 1, x minus 1, 1 over h, or it's h on the bottom. Reciprocated this one, multiplied. H's cancel. Negative 1 over x plus h minus 1, x minus 1. H goes to 0. What I'm left with is negative 1 over x minus 1 squared. That's the derivative. Slope of the curve at any given point. The algebra part's the hardest because it's a lot of writing. And that's where the most mistakes occur. I'll show you another method of taking these, an alternate method of finding these same limits.
So let's write this.
Hopefully. So in our function, we start off at x, we go to x plus h over here somewhere, right? So this whole distance here is h. Instead of writing x plus h, we write z. Originally, we had f of x plus h minus f of x over h as h goes to 0. That's the original. Now the alternate method, instead of x plus h is equal to z, so it's f of z. It's f of x. So what's h equal? From this here, what does h equal? Work it out. I mean, it's not calculus.
Why?
Z minus x. Work it out. Solve for h. So we got rid of the h. Now, you see how we use h goes to 0 up on the top one because h is the denominator? Now we have z and x on the bottom. So our limit is as z approaches c. Remember, z is this second point right here. As it approaches x, the limit gets smaller and smaller and smaller and smaller and smaller and smaller and smaller. Let's look at it. Use the alternate method using this function.
inside X.
Right, because Z equals what?
C.
Look at your notes. What does Z equal? X plus H. It takes the movement from wherever my initial X is, however far H is, that's where my Z is going to be. So the next point is f of Z. So now the limit as Z approaches C, radical Z minus radical X over Z minus X. It is. I mean, we've done it, but we did it with a lot of writing. We had the X plus H everywhere. So what do we do now? Sorry, not C. This is X. I'm sorry, is X. Because the value, the point we're looking at is the X value. If we set Z equal to X, what do we get? You're guessing. Look at the equations. Stop guessing. If Z becomes X, what happens? 0 over 0. Radical X minus radical X is 0. X minus X is 0. I mean, look at the equations and plug in the numbers. So how do we fix that? Multiply with the conjugate, which is radical Z plus radical X, radical Z plus radical X. What does the top become? Z minus X. Radical Z times radical Z is Z. The middle points cancel. Minus radical X is X. Anybody want me to FOIL that out for them? Or is everybody okay? It's the difference of two squares. On the bottom, we have Z minus X, radical Z plus radical X. Can't do anything else, so when Z becomes X, what do we get? If Z becomes X, anywhere you see an equation, anywhere you see a Z, put an X in its place. Radical Z plus radical Z is 2 radical Z, or 2 radical X. When that becomes X, we're adding those two together. It's a lot less writing. So you can always use this method, but you have to remember when you change Z, you also change the limit values. From instead of H goes to 0, now Z goes to X. It's a lot cleaner. Let's look at different notations, the way we can write the derivatives. We know that's the first one, f prime of x. These all mean the same thing. The next one we have is y prime. Remember, y is equal to f of x. So if I take the derivative of y, I also take the derivative of f of x, I take the derivative of y. The derivative of x with respect to the derivative of x. df dx. The derivative of the function of f with respect to x. The derivative of f of x with respect to x. All of these symbols mean exactly the same thing. They all mean the derivative. For example, let's say we had a function. We have a three-dimensional function. Z is equal to some function with x and y in it. I can write something like this. Well, in the first part, I'm taking derivative of the function only with respect to x. And this one only takes with respect to y. We'll see these kind of equations towards the end of the semester, and definitely in Calculus 2. Notations at an x value. So the first derivative f of x is equal to dy dx at x equals 0, or when x equals 0. Or the derivative of the function with respect to the derivative of the x at x equals 0, or when x equals 0. Again, it doesn't have to be 0, it could be at any point. For example, the one we had earlier, the derivative of radical x with respect to x when x equals 4. These are all sorts of different ways you could symbolically represent the function of derivative. Okay. Let's look at on one-sided derivatives. Differentiate on an interval one-sided derivatives. Do you think we'd have one-sided derivatives? Why did we take one-sided limits? Remember this function? Because we were bounded. Our domain of our function was from -2 to 2. So at -2, we couldn't take a limit as x approaches -2 from the left, because nothing exists. So in order for this to determine whether it's continuous in that domain, at the endpoints, we look at as x approaches -2 from the right, and as x approaches +2 from the left. We do the same thing with derivatives. Because if a function's differentiable, it's got to be differentiable anywhere. But if we have a specific domain, an interval that we're looking at, then we have to make sure that the limit exists at every point in that domain. So that's what we're looking at next. I equals f of x is differentiable interval AB if it has a derivative at each point on the interval. How would you determine if it has a derivative at each point on the interval? Well, the limit has to exist at each point inside A and B. What happens as we get closer to the endpoints? We can no longer take two-sided limits, we can only take one-sided limits. The function is differentiable a closed interval AB if it is differentiable at each point of the interval AB. And I'll make this open interval for these guys. And left and right limits exist at the endpoints. other words, the limit as h approaches 0 from the right, a plus h minus f of a over h exists, and the limit as h approaches 0 from the left of f of b plus h minus f of b over h exists. These are all called the right-handed and left-handed limits. See an example here. Which one do I want to do? Value of x. Let's look at the function f of x equals absolute value of x. The absolute value of x. Where is it differentiable for sure? Sure? Again, you spent these answers pretty quick without thinking about them. About them first. What does the graph look like? Right? So we know the function looks like this. What do we know? From negative infinity to 0, what happens there? Does it exist? What is it? The limit as x approaches 0 from the left of the function what does that equal? Does the limit as h approaches 0 from the right of our function what does that equal? What's the limit? You're asking a question. If you're coming from the right, where are these values heading? As x gets closer to 0, where are these values going? They're going to 0 also. But, how about differentiability? What's the difference between the limit and differentiability? The limit has to approach a value. So we can say that the limit as x approaches 0 period is 0. So does the limit exist? Yes. But is it differentiable at all three of those points? Why not? Again, if you're going to answer, you're going to tell me why. The why is the most important part of math. What does differentiability find? You take a derivative, what are you finding? Slope. Slope of the curve. On the left-hand side, what's the slope of the left-hand side? -1. It's going down. As x gets larger, y is going down. From the right-hand side, what is the slope? +1, because as x goes to the right, it's getting higher. The positive slope. Are the two slopes the same? F1 from the left doesn't equal F prime from the right. 1 equals -1, 1 equals +1. So it's not differentiable, because what happens at 0? What's the slope at 0? It's a horizontal line, so it's 0, yeah. This is why we're going to talk about, we're going to try to define differentiability, smoothness, and continuity. There are certain points, certain type of functions that are not differentiable. So, this is a very important concept. But remember, it has to be on an interval, AB. The limit exists in that interval, but it's not differentiable inside that interval at every point. Let me see another example. Oh. My favorite. What does that function look like? The Atari symbol, right. It gets infinitely close to 0. The limit as x approaches 0 from the left, what's the limit? Yeah, it's going towards infinity. As x approaches 0 from the right, where is the graph going? But look at the derivatives. The derivative of the function from the left, is it positive or negative? A slope as x gets in is going to infinity. Is the graph getting higher or lower? So the slope here is positive. This one's greater than 0. On the left-hand side, as x gets larger, y gets slower and smaller, smaller. So here, the derivative is negative. The slope is negative. Does the derivative exist at 0? Because one side's positive, one side's negative. So there's another example when it doesn't exist. So let's look at the conditions where derivatives do not exist. When are functions not differentiable? At corners. They're not differentiable at pointy edges, at corners, at points like that. As we just look at the Atari symbol, the 1 over x squared function. At vertical tangent lines. What does a vertical tangent line look like? Right up and down. Remember, the function's got to be continuous. It's got to be differentiable throughout the inner. So, at one point and another. Because at one point, the slope changes, and eventually we'll have a vertical slope. What's the slope if it's vertical? What's the slope designation? Infinity. It's also does not exist or undefined. But whenever you have vertical lines, vertical slopes, they don't work. They're not differentiable at that point. At discontinuities, what's a discontinuity? What's an example of a discontinuity? We had those examples, actually one of them were the first examples we used in this class. For example, if we had like that, that's a discontinuity because it's continuous here up until the point C, and then all of a sudden jumps up and it regains continuity. Another example is the step function, the greatest integer function. And the last one is wildly oscillating. 18. Wildly oscillating. What does that mean? Wildly oscillating. Yeah, it starts and then it goes just wildly at both ends. For example, the function x sine x. Can you think of any trig functions that are not continuous, that have holes, that have spaces? Why tangent? Yes, tangent is one of them, but you tell me why.
It looks like a
In trigonometry, there are only two functions that are universally continuous: sine and cosine. Sine of x is between -1 and 1, and it goes infinitely in that oscillating function. Cosine same thing. It doesn't stop. It goes on forever. Tangent, secant, cosecant, and cotangent are all rational functions. Tangent is made up of sine x over cosine x. Cotangent is made of what? Good. Cosine x. So what happens? Can the denominator ever be undefined?
No.
Yeah. Whenever or cosine is 0, the function is undefined. So it has asymptotes, which means they are not continuous at those points. Same thing with the sine function. Whenever it's 0. Secant is 1 over cosine. Whenever cosine is 0. So whenever you have rational functions, whenever the denominator equals 0, the function is not continuous at those points. So, differentiable functions are continuous. A function is continuous if it is differentiable at each point in the domain of the function. Here's the first theorem. Differentiability implies continuity. What does that mean? Differentiability implies continuity. If it's differentiable, what does that mean? If the function has a derivative at x equals c. Why do we use x equals c? Because remember we do the limit function, it's always x approaches c, and absolute value of x minus c is less than delta. If a function has a different derivative at x equals c, then the function is continuous at x equals c. Because in order for it to be have a derivative, it has to have the limits. The limits have to exist, and for the limits to exist, they have to approach from both sides, and the limit of the function has to be the same as the two sides approaching. All that stuff we did in chapter 2 is now coming together. Let's look at some examples. Four minus x squared. Find these values. It'll be very healthy for you all to memorize this. We're going to see a lot of those in this course. A plus b squared is a plus a minus is a squared minus. So it'll just be a shortcut for whenever we do these. We'll just plug it in there. Well, we distribute that. Minus x squared minus 2xh minus h squared. Distribute the other one. 4's cancel. The x squares cancel.
And all those feed to that.
Mm-hmm. This is what f of x equals. F prime of x. So when x is -3, what's the answer? +6. When x is 0,
0.
when x is 1, those are your answers. One more. And you guys are getting much faster at this. And next week, when I show you the shortcuts, you're going to do 100 times faster than this. Next week was, well, we might get to it Wednesday. Okay, the function is x plus 9/x. Find f prime of -3. Yes. What's that? Oh, crap, yeah. Okay, I'm sorry. Oh, shoot, yeah. I keep on thinking we had 250. Okay, we'll pick up from here next time.
Okay.
All right, everybody.